Okay, so good morning, everybody. Thanks, Andre, for the introduction, for being ahead of time. That's very good. Thanks also for the invitation, of course, and also for the organization of the workshop and for the hospitality yesterday, especially. So, okay, so the title of my talk is not exactly what it is about, let's say. So I changed the topic slightly, partly because our work on spin dynamics is in collaboration with Peter Oppener, and he showed already part of this work yesterday. So I will, in the first part, I will talk indeed about the ultrafast switching in chromium platinum with the inverse Faraday effect, but then I will talk about a rather new topic in our group that will also be interesting, I hope, for this community, namely the transfer of angular momentum from the spin system into the lattice. Okay, so the first part is in collaboration mainly with a group of Peter Oppener, and it is on switching in antiferromagnets with the inverse Faraday effect. And we took a certain system as an example there. So I think I can skip the introduction to the inverse Faraday effect. Mainly it appeared several times yesterday. So what we think is that in some materials in ferromagnets, the switching is that mostly that with the action of the laser pulse, we demagnetize the sample. So thermodynamically, you could say the magnetization goes through zero. And then the inverse Faraday effect, it might be a small effect, but it changes the probabilities to recover in the one or the other state of the ferromagnet. So you get something like a probabilistic switching, at least in small nanoparticle systems. So the question now is, what about antiferromagnets? So we chose chromium platinum as an example here. Chromium platinum is a simple antiferromagnet for a theoretician. It has two sublattices, so with equal magnetic moments on the chromium sides, and they look as shown here, two sublattices to the right or to the left. Okay, so now in Peter Oppener's group, they did calculations of the inverse Faraday constant, which is shown here. It is frequency dependent, and it is different on the two sublattices that is shown here in yellow and in blue. And the most important message is that at some frequencies, it has even different sign, which means it is staggered. It is not exactly antisymmetric, by the way, but it has different signs. And that means that when we come with a circularly polarized laser pulse here, then you get induced moments. That is the nature of the effect on the two sublattices, and these two moments can point in the opposite direction of the magnetic moment. Okay, so now we get a new equilibrium configuration that can lead to switching. There's also a transverse effect. I just mentioned that if the laser pulse comes perpendicular direction, the effect is tiny, let's say, but it's not zero. Okay, so what we did is then spin model simulations, which means we try to implement this effect in the spin model. A spin model for chromium platinum would be, the simplest model would be some exchange interactions that we calculated from ab initio methods. Some anisotropies. It is an easy plane antiferromagnet with an additional cubic anisotropy, so that it has four stable states for the Nail vector in plane, let's say. And we model the inverse Faraday effect as an additional magnetic moment on the sides. So we say there's an induced moment in addition to the local magnetic moment. We transfer that somehow to normalized vectors and so on. We can estimate the strength from this formula and from the ab initio calculations. And yeah, then we also have to model the action of the laser in terms of heating. And we do that by estimating the electron at the phonon temperature with a simple electron to temperature model. So we get something like that. The laser pulse comes, the electron temperature goes up a lot, heats the material, goes down. The inverse Faraday effect has some dynamics. It goes up with the laser pulse. We also have to assume that it decays then on some time scale, some 100 femtosecond, as shown here in the induced moment. That is this red curve. It is multiplied by a factor of 100. So that means in terms of a normalized magnetic moment, it is less than 1%. It's small, but in this Heisenberg exchange here, it comes with the exchange constant, so it's not neglectable. And then you see that because of the heating, you will have a demagnetization, or the Nail vector goes down, then recovers as usual. That also a ferromagnet would do, but also it can switch. So that means with the inverse Faraday effect here, we see a switching, and that is on an amazingly short time scale, some 100 femtoseconds only. So we did these simulations with the Landau-Dietrich equation, the stochastic version of that. I just mentioned that, but I think it popped up yesterday already. So it's this equation with precession, dissipation, and then also fluctuations. And we do that for a lot of magnetic moments to get the statistics right. And the statistics is important. So there are probabilities of switching, and that's what we have to analyze. And that is what my PhD student Tobias Danneger did, and it's published here, and he's also here in the audience, should be at least somewhere, and here's a poster somewhere there at the end on this. So that is now the statistical analysis of the switching probability here over the laser power. The transverse effect is small. That means this is zero effect, you could say. Zero effect means for low laser power, nothing happens, no switching probability. For a very high, you just randomly switch. Okay, so you get, let's say, 50% switching probability. That's just a random event. So that is no effect, okay, or only heating effect. But with the inverse Faraday effect, you get curves like that. For example, the blue one here, that means in between no effect and just random heating, you can get a very high, close to 1 switching probability, which is deterministic switching. And the next question is, why is it so quick? That's not easy to understand. So we compare here iron platinum with ferromagnet with the chromium platinum. So a ferromagnet, as I said already, that is linear switching. It demagnetizes and then comes out on the other side with some fluctuations. On the other hand, chromium platinum switches via this elliptical path. So it does not demagnetize during the switching. It does not. The thermal effect is not so big, not necessarily so big. Instead, you get a kind of precessional motion, one could say. And that is like often in antiferromagnets, you get an exchange enhanced switching. So first oops, what is this? First oops. I'm not sure what happened. Maybe something with the Zoom session or so. First, the precessional part of the torques moves the two sublattices magnetizations in the same direction. Then you get some tilting, and because of the tilting, you get a torque that directly switches both sublattices equally, and then you end up in the switch state. And that takes because the torques are so big. Because it's not the damping torque, it's the other one that is so quick. There are also other effects, additional ones you can discuss with Tobias, like 90-degree switching and so on. Okay, that was this part on switching. We have, as I said already, also other work that was introduced already yesterday by Peter. But I also wanted to talk a bit about this spin-lattice interaction, because I think that is a very nice subject that we are working on increasingly. And we started this work in connection with Peter Baum. He's a new colleague of mine, an experimentalist in Konstanz, and he works on ultrafast electron diffraction. And I discussed with him once this very old riddle, one could say, namely the ultrafast demagnetization, say in nickel. Where is the angular momentum on a time scale of some 100 femtoseconds? So if you believe the angular momentum should be conserved in the total system, the demagnetization corresponds to a decay of angular momentum in the spin system. So where does it go to? And we follow this idea that it might go into the lattice quicker than many people thought. And that is his expertise. So he performed ultrafast electron diffraction. That is a pump probe experiment, you could say. So we have nickel here, you pump as usual, you say you demagnetize by 50%. And then with the electron diffraction, you can get the information on the lattice. So you get Bragg peaks that tell you the lattice structure. So it's a single crystal of nickel. You get a nice, according to the cubic lattice structure, you get a nice Bragg peak pattern. And now, if you heat the phonon system, you could say you get a broadening of the Bragg peaks, and that's what you can measure. the decay of the central intensity. That's a measure of the broadening of the Bragg peaks, and that is a measure of the atomic motions. And what you see is this here. So on a very short time scale, it starts some 100 femtoseconds, you get this broadening. That means the lattice moves. Okay, but we wanted to go further and show that it takes not just energy, thermal heating, but the angular momentum. And that's our idea. So the theoretician's view is if you demagnetize and the angular momentum would go directly to the lattice, then you would have something like atomic motion, like this here, a local transfer of angular momentum. So the atoms start to move on an orbit around their equilibrium position. And only on the longer time scale, say, you would get this phonon excitation, let's say, would decay into a global motion, a global rotation of the sample. That would be the Einstein-de Haas effect. So the demagnetization goes into a sample rotation. But that cannot happen on a time scale of some 100 femtoseconds. That's impossible. But this local effect could happen. And that would mean that you excite phonons with angular momentum. So these two transverse modes that are phase shifted, that would locally be a rotation of the atoms. Okay. And we simulated that with the molecular dynamics. So that's not spin dynamics. Okay, now we model the molecular motion. There are software packages for that. So we used LAMPS. That is a free molecular dynamics code. And what we did is we simulate nickel with the realistic lattice potentials. And then we calculated how much motion we would have. So if you demagnetize 50%, you can calculate the angular momentum, some h bars. It is like every seventh atom would get one h bar from the spins, okay? And h bar you can transfer to displacement times velocity. That gives a rather small displacement. It's not a very high excitation. But you can do that, you simulate that. And the interesting point is that you get an anisotropy now of the motion, because if you have the magnetization in one direction, okay, so the angular momentum would be in the plane, the angular momentum would be aligned with this direction, and the motion, the displacement and the velocity would be perpendicular to the spin direction, okay? And that means if you come with an electron beam from the top, for example, then normally equivalent Bragg peaks must become anisotropic, because the motion is only in this plane. Let's say the electron beam comes from here, you have the Bragg peaks. So the X and Y direction should be different, okay? And that is here, I'm not sure if I get rid of this. Okay, anyway, so so that is our simulation. So we calculated the anisotropy, or the fraction of nominally equivalent Bragg peaks because of the motion in our molecular dynamics simulations, okay? And that is then the measurement. So they tried exactly the same thing. What they did in the experiment is they, with an external field, they moved the shift of the magnetization, pointing once in plane in this direction or in that direction. Electron beam comes from here. And that means because of this polarization of the phonons, you get an anisotropic contribution to the broadening of the Bragg peaks, okay? And that's the measurement here. It is even quantitatively equivalent to our simulational forecasts, you could say. It's a small effect, but it's there, and it's amazingly quick. As we say, it takes only some 100 femtoseconds. That is the time scale of the demagnetization to appear. So our conclusion is that while the magnetization, while the sample demagnetizes, already some motion in the atoms appears on the same time scale that takes over the angular momentum. That's of course, and only on a longer time scale, I should say, then these phonon system would somehow decay and the sample would rotate. If it is free flying, of course, in the experiment, it would be on a substrate, you get strain waves, things like that. They were also measured some 2 years ago. So in this group here, they called it ultrafast Einstein-de Haas effect. And that was a measurement of, you could say, a strain wave of the sample. So what we think is that locally first you have this excitation of phonons. That opens up, of course, a route of a lot of possibilities what you could do. So what we think is one can obviously excite these phonons. They have angular momentum. Maybe one can even transport them So what we would need is measurement techniques to produce them. Okay, that exists. Maybe also to transport phonons, and then they could once again be transformed maybe into spin in a magnetic system or things like that. So I think that this is really a playground for the future. Maybe, okay, coming back to antiferromagnets. So there is also now the idea, if that is a bottleneck for the demagnetization, namely the excitation of phonons, it could be faster naively in antiferromagnets even, because there you don't have to transfer globally angular momentum because it is zero anyway in antiferromagnet. I'm not sure that is a very good argument, because I would also argue that locally there should still be some coupling or so. But anyway, we did some simulations again with the spin model. It's also done by Tobias, comparing ferro and antiferromagnets, just the demagnetization. And amazingly, even in the spin model, there are no phonons here at the moment. An antiferromagnet demagnetizes quicker than a ferromagnet. And this is it's a very simple theoretician's model of an antiferromagnet. It's just some exchange, a kind of cubic structure. We keep all parameters identical except for the sign of the exchange constant. And with that, we can create a ferromagnet, a layered antiferromagnet, or a cubic antiferromagnet. And you see the demagnetization times following a laser pulse are already different by a factor of, I don't know, something 5-4 or so. And that is only Landau-Lifshitz. There's no phonons here, okay? That is only, I would say, it means that there is an exchange enhancement, even also because of the noise contribution to the demagnetization also. But we think in reality it should be much more interesting with if we would take into account the phonons explicitly. And that is the last part of my talk. So we are also interested now in new ways to calculate the spin and molecular dynamics at the same time. And that is a collaboration now with a group of Hubert Ebert and Sergei and Svetlana, also here in the audience. Somewhere there, there is also a poster on their work on the floor below us. Okay, so we are now, the point is what we would like to do in the future is that we solve a coupled equations of motion for the spin and the lattice at the same time. So that is a rough view of what we intend to do. So there exists software for solving the Landau-Lifshitz equation, and we are, my group is specialists in that. But there's also this work on molecular dynamics that you showed you, and I think we should connect that in the future. Spin lattice molecular dynamics, and to make that even more interesting, especially the nature of the coupling. To understand the nature of the coupling, we also need information from first principle calculations. And what I can give you is more the idea what we are working on currently. So it would look like that. You write down a Hamiltonian that has spin degrees of freedom and the spatial degrees of freedom. Lattice positions and momenta, okay? And you say, okay, there is a spin model, say a Heisenberg exchange, whatever. There is the usual lattice potential and kinetic energy for the molecular dynamics, plus we need a coupling between the degrees of freedom. So there must be a part of the Hamiltonian that has spatial and spin degrees of freedom, okay? You can do some assumptions, make some assumptions. Many groups at the moment work on that. We did that also in the past. Then it looks like in the movie here. Maybe I scrolled it back so that you can see it better. This is a coupled spin molecular dynamics simulation. So the spin is color coded, and the lattice motion you can see directly. So we start simply here with some. Oops, can I grab that? With some non-equilibrium situation for the spin, something that must relax. And what you see is it decays into a Magnon system, okay? And then if you look at it, the Magnons exchange angular momentum with the lattice, and now the lattice starts moving. So you see also a bit of phonon system, one could say. And if you look at it carefully, the angular momentum of the spin system was not constant. So the sample starts rotating. It takes a bit of a while, but okay, so we did it like that. The coupling, you see it starts now to rotate. It's a free flying object in our simulations. So that is here, well, maybe a first movie of a coupled spin lattice and molecular dynamics. But we have lots of problems with that, so we are working on that. And there are many open questions. And one, the most important for the moment, is what exactly is a good form for this coupling term. So how do spins and lattice degrees of freedom couple microscopically? There have been some ideas in the literature. So people in York work on that, Roy Chantrell's group. They assumed, as we did in this that's our first work, dipole-dipole interaction that has spatial and spin degrees of freedom, but that is not the reason for anisotropy. So there should be other terms as well. And that's what we are working on with the group of Hubert-Ebert currently. So they suggested a certain term that also was already out in the literature, namely that you kind of expand a spin model parameters with respect to distortions of the lattice. Okay, so the first term is, let's say, a general type of interaction. So the diagonal part of that would be Heisenberg exchange, of diagonal would be whatever, anisotropy or Jaruzelski-Moria. And then you say, okay, now you expand with respect to small displacements. So the next term looks like it, but it assumes that atom K is displaced. Okay, so the idea is you have spin-spin interaction as usual, but now you say, okay, a third atom, maybe the next neighbor to the right or so, is displaced from its equilibrium position. What does that change? It changes a lot because it breaks symmetry, for example. The reason that we don't have Jaruzelski-Moria in cubic crystals is the symmetry. If you displace one atom, you break inversion symmetry. So now you get new elements in your exchange tensor. Okay, so it is a three-body thing. Okay, of course there's also IIK interaction or IJI or whatever. So two spins, the interaction changes because that atom is displaced and so on. And they, in Munich, they found a new scheme to calculate this. It is like, you could say it's like the Lichtenstein formula that you might know for the Heisenberg exchange, but now generalized for this displacement of a third atom. So they can calculate that. Now I show you here first results. As I said, there's a poster there. These are first results for iron. Okay, there are lots of numbers, of course. We look at this here, the first linear term in displacement, and it is an IJJ. So two-body interaction. It's the change of this exchange matrix because one of the two interacting spins, the atom is displaced. Okay, and we are currently working with that. There are now millions of numbers. You can look at it, but maybe one central message: if you just look at how big the numbers are, the leading contribution is this here. That is the isotropic part of that's the normal Heisenberg exchange, you could say. That changes if you displace one atom. Okay, but this one here does not transfer angular momentum. It would transfer energy. You could say it's a magneto-volume effect, but since Heisenberg exchange is isotropic, it does not transfer angular momentum to the lattice. The leading part that transfers angular momentum is this here, and that is the antisymmetric off-diagonal part. So you could call that Jaruzelski-Moria interaction. And that is the biggest contribution here. This one is the biggest number. The other are contributions to the anisotropy, you could say. Okay, they are smaller. So in a nutshell, what we found out is that even in a cubic crystal that doesn't have Jaruzelski-Moria, because of the distortion of the lattice, the Jaruzelski-Moria interaction would appear. This is the leading part that transfers angular momentum to the lattice. Okay, so, and we are working on that continuously. So we would now like the next step to put this in this framework, in our software to solve the coupled equation of motion numerically. But there's still some conceptual problems, but I don't have the time here to go into the details. So with that, I'm at the end. So I just thanks my group, of course, who is doing this work, and also my collaborating partners. Maybe I use that slide also for the summary. So there is Peter Oppen, Uppsala. We work a lot together, and I showed these results on the inverse Faraday effect here. There's Peter Baum from our university, Konstanz, who did this electron diffraction experiments, and there's a group of Hubert-Ebert in München, where we now work on regarding this spin lattice molecular dynamics. And with that, I'm at the end. So thank you for listening.